Hi, my name is Omar. Today I'll be talking to you about visible ranks of code with locality. And this is joint work between me and Guruswami. So the notion of locality in error correcting codes refers to the idea of recovering a single code word symbol from a small number of other code word symbols. So formally speaking, if I have some code C and a code word C in it, the ith position Ci in the code word has collections of groups of other code word symbols, such that if I know the code word symbols in, say, for example, Ri1, then I'm able to determine what the value of Ci is. So to illustrate this point, consider this picture here. So if I know these symbols in Rij and I know what the values are, then I'm able to use a sum function that computes the value of Ci here. So we call the collection of code word symbols Rij the jth repair group of Ci, as it quote unquote repairs Ci when it's damaged. And there are many ways you can add constraints on the Rijs, and because of that, there are many different kinds of codes with locality. And the applications range from distributed storage systems to probabilistically checkable proofs and private information retrieval. So in this talk, we're going to restrict our attention to linear code C, and moreover, we're going to be interested in two kinds of locality codes. First, we're going to be interested in DRGP codes. So in such codes, each position Ci has T disjoint repair groups, where T is going to be a constant here. And because they are disjoint, that's why DRGP stands for disjoint repair group property. The other codes we're going to focus on are locally correctable codes. So each position Ci has a linear number of disjoint repair groups, linear with relative to the code word length. Okay. Moreover, each repair group has size at most q. So as for bounds, we know an upper bound on DRGP codes of at most n minus squared n. As for lower bounds, we know constructions that get n minus t.585 root n. And the major challenge is to show that if there's a way you can add a t in the known upper bounds. Okay. As for LCCs, we know for q at least 3, I should add it here. We know that the rate of the code is at most n to the q minus 2 over q minus 1, whereas the dimension of the code is at least log to the power of q minus 1 of n. Okay, and so there's an exponential gap between the two bounds, and it's a major upper question to improve any of those two. So in this talk, we're not going to look at the dimension of the code, but we're going to look at the redundancy of the code. So we're going to focus on this table above here, and all these bounds basically translate from upper bounds to lower bounds and vice versa. And we're just going to take n minus these values here. So for example, n minus squared n here is going to be just squared n, and so on. Okay. So these are the bounds here, and our hope is just to improve on the lower bounds on top here on the second row. So our plan to do that is to build a combinatorial / linear algebraic framework for it, and then we're going to analyze natural combinatorial lower bounds arising from this framework. So let's motivate the framework that we're going to build. So suppose that the jth repair group of I just remembers the code word symbol I. That's only possible for linear codes if and only if there's a code word Cij in the dual, such that I's contain the support of this dual code word, and the support of this dual code word is contained in an I union the jth repair group of I. The second observation is any linear code can be expressed as the kernel of its parity check matrix H. And finally, H repair the repair group condition is the only condition for DRGB codes in LCCs. So that's the only thing we have to work with for these codes. So the idea is if we just let the rows of H be exactly these dual code words, then a code is DRGB / LCC if and only if it's in the kernel of this parity check matrix H. So we just focus on this matrix H that is just basically has such supports of Cij. So it's really just a question of a matrix H with 0 and non-zero entries in some special way. So that leads us to the idea of stencils. So a stencil is a matrix of zeros and stars, where the stars denote necessarily non-zero entries. They must be non-zero. And the goal with stencils is to replace these stars with non-zero entries in some field F of your choice, such that the rank of this matrix is minimized. And we call this minimal value the F rank of H, and as denoted as rank F of H. And because stencils are such a natural framework, it has many connections to things such as unique restricted matchings, matroids, and so on. Okay, but our focus here is stencils and locality codes, particularly DRGB and DRGB codes and LCCs. So how can we connect these two notions more formally? So first, let me define the idea of DRGP stencils. So a DRGP stencil is a 2n by n stencil where each column I has two rows which supports AI union I and BI union I, where AI and BI are disjoint. Okay, so for example, in this 2 DRGP stencil, these first two rows share the element share the support at the first element, but they're disjoint every other place. So two DRGP codes are essentially equivalent to DRGP stencils in the following way. If we replace the entries in the two DRGP stencil H to obtain a matrix M, then the kernel of M is exactly a DRGP code. So now our goal, if we want to get lower bounds on DRGP codes, we just need to get lower bounds on the F rank of two DRGP stencil H. So now the question is, can we find some natural combinatorial lower bounds on the F rank of H? And visible rank is going to be one combinatorial lower bound we're going to look at. So to motivate the idea, let's just focus on a simple question here. So suppose I give you a square stencil H. Instead of asking you what the lowest rank it can get, let me ask you. Let's ask if it can even if it can get an F rank that is even lower than its full rank. So to do that, if you want to know if a matrix is full rank or not, we just look at it by the Leibniz formula. We just have to look at its determinant. So by the Leibniz formula for determinants, we know that determinant A is just a summation of its general diagonals. So now let's just case on what these general diagonals look like. So the first case is if matrix A has more than one non-zero general diagonal, then we can't really guarantee that the determinant is always non-zero. Okay, because these general diagonals have a chance that they can cancel out with each other. On the other hand, if all the general diagonals are zero, then the determinant is going to be zero by the Leibniz formula. And the last case is A has exactly one non-zero general diagonal, then none of these general diagonals cancel out. There's just one general diagonal, and because of that, the determinant is always going to be non-zero. So the answer is if a stencil H has exactly one general diagonal of stars, then it's always going to be full rank, no matter how we replace the star entries in it. So such stencils are called visibly full rank. And that brings us the idea of visible rank. So the visible rank of a stencil H is the largest square substencil in it that is visibly full rank. By substencil here, I mean just a restriction of H to some of its columns and some of its rows. And we denote this value by VRK of H. And by our previous discussion, we can see that the F rank of H is at least the visible rank of H. So now how good can the visible rank give us improved lower bounds? It actually doesn't. So for DRGB codes, we showed that that there are DRGB stencils H with a visible rank of t squared log n. So compared to the lower bounds that we know for DRGB codes, there's an exponential gap between the two things. So visible rank performs terribly for DRGB stencils. On the other hand, for LCCs, we can find LCC stencils with visible rank at most n minus omega O of n to the q minus 2 over q minus 1. So it matches the known lower bounds that we know of. So we can find LCC stencils that match it, and we get no better improvements. Okay, so let's just give an outline of the proof. So we have a nice lemma for visibly independent, visibly full rank stencils. So if I have a square stencil H with exactly one general diagonal of stars, then we can permute its rows and columns such that it becomes an upper triangular stencil. So because of this really nice structure, we have a good sense of what these visibly full rank stencils look like. So if you consider a random DRGB stencil and a random LCC stencil, then using this nice upper triangular structure, we can show that the chance that any substencil is visibly full rank is really small. And because it's really small, we can just apply a union bound over all possible substencils, and then by then we have shown that random DRGB stencils and LCC stencils attain the bounds that we have shown here. All right. So visible rank doesn't give any better bounds, but can we still hope for better combinatorial lower bounds? So that leads us to tensor products. Yeah. So here's an observation. If I have some matrices M and N over some field F, the support of their tensor is completely determined by their initial supports. So we don't have to know what the non-zero entries of M and N are. So the idea is we can also define tensors for stencils too. Formally speaking, if I have stencil H1, H2, its tensor is defined by the following formula, but this just follows naturally from how you do tensors for general matrices. And the nice observation about this is that for stencils H1, H2, we have that the visible rank of their tensor is at least the product of their visible ranks. So in other words, visible rank is super multiplicative, whereas the f rank is actually sub-multiplicative, and it becomes smaller over time. So in other words, the f rank of h1 times the f rank of h2 is upper bounds the f rank of their tensor. So we can combine these inequalities when h1 equals h2 and a equals h, and inductively use them. And what we get is that the kth power of the f rank of h is at least the f rank of its kth tensor power. That's at least the visible rank of the kth tensor power of h, which is at least the kth power of the visible rank of h. And this in particular means that the f rank of h is lower bounded by the kth root of the visible rank of the kth tensor power of h. That's at least the visible rank of h. So we know that this bound is better than the visible rank of h, and it's still lower bounds f rank of h. So now we got better combinatorial lower bounds on the f rank of h. More generally, we define the visible capacity to be the supremum over all these possible new combinatorial lower bounds. And because of our previous discussion, we get that the f rank of h is lower bounded by the visible capacity. And one of our big questions in our paper is does there exist a stencil h for which its f rank is strictly greater than its visible capacity for every field f. But now let's just focus our attention to tensor powers and locality. Okay, so do these new combinatorial lower bounds give better improvements on the redundancy of DRGP codes in LCCs? And here's what we show. We show that for any DRGP stencil, we recover the known lower bounds of the redundancy of DRGP codes, and we get that the f rank of h is always at least square root n. So more generally for stencils, not just for DRGP codes, we can find stencils for which the visible rank of h is log n, but the visible rank of its second tensor power is linear in n. So there's an exponential gap between the two things. And that is quite interesting. We also have a question of whether you can also do this for t tensor powers instead of like the second tensor power. Now for LCCs, we show that there are LCC stencils H for which these bounds only improve this small value. Reduce the small value here by a factor of k. So if k is like subpolynomial, then we really get no polynomial improvements to current bounds. So unless you take like a polynomial tensor power, we get no better improvements. So let's sketch the proof for DRGP. So the proof is just a simplified version of the known proofs. And it goes as follows. So suppose you have a 2 DRGP stencil H, where we index the columns from by 1, 2 to n, and it's rows by alpha 1, beta 1 to alpha n, beta n. Then we know by the DRGP property that the support of alpha I and beta I intersect at exactly I. So now if we consider the tensor product H tensor H, let's consider this following specific substencil. It's the substencil where the columns are 1, 1, 2, 2 to n, and its rows are alpha I, beta I. And because of this support property, we deduce that this substencil is exactly general diagonal of stars. And thus we find that the visible rank of H tensor H is at least n. So that finishes the proof. For LCCs, we have this lemma that says that if you have the stencils A and B, then the visible rank of A tensor B is at most n1 times the visible rank of B, where n1 is the number of columns in A. So for this lemma, if we inductively use it for an A is equal to B, then we get that for any stencil H, we have the visible rank of the k tensor power of H is at most n to the k minus 1 times the visible rank of H. So this is the lemma that we're going to use for our proof of LCCs. So we know that previously that we can find LCC stencils H for which its visible rank is equal to the known lower bounds on it. And so therefore, if we just use this inequality and then just use some the Bernoulli equality here, we just get the result as here. So these are all the calculations. So this isn't just generally a result for LCCs. This is a result for high redundancy codes. So if you have a code with a high redundancy of n minus the little o of n, then the kth root of the kth root of the visible rank of the kth tensor power does not give any better improvements for any constant value k. So you have to take an asymptotically growing tensor power to show any better improvements. Now that we've shown that, these new combinatorial lower bounds, these tensor power lower bounds, recovers the lower bounds known for the DRGP codes, and the bound does not improve for LCCs. But can the visible rank still recover the known lower bounds? We show that it cannot improve on them, but can it still recover it? That's what we're gonna talk about next. So to do that, first let me introduce the notion of spanoids. So to understand spanoids, think of the set 1, 2 to n as a collection of logical statements. And so a spanoid is just a collection of inference rules from some subset S of n to some element I. Okay. So so for any for a set T and an element I, we can derive the logical statement I from the collection of logical statements T by a sequence of inference rules where each set Sj is just a sub collection of all the logical statements that we've deduced thus far. So for a set T, we define its span to be all the elements in N that we can derivable starting with T, and we denote the rank of the spanoid as the smallest possible set for which it can derive all of the set N. The spanoids were introduced by De Beer, Gopi, Gu, and Wigderson as an abstraction of LCCs, and they show that for Q at least 3 QLCC spanoids have rank at most known lower bound. So the upper bound on the dimension of LCCs also holds for LCC spanoids more generally. And for Q at least 3, they construct LCC spanoids matching the upper bound of the dimension of C. So why do we talk about spanoids? First, let me introduce the idea of symmetric spanoids. So a symmetric spanoid has subsets S1 to Sm of n, and all of its inference rules are the form Sj minus I reduces I for any element I and Sj. That is, if we know all of S of the set Si except one element Sj, then we can deduce that final element. So we prove an egg nullity theorem between stencils and symmetric spanoids. So in particular, if we have a symmetric spanoid S, we can find a n by n stencil H such that the sum of the rank of S and the visible rank of H is equal to n. So sometimes HS is the parity check matrix of S. So the idea is just to let the ith row of H be the set Si, and then we just show that for any set T that spans all of n, that's only possible if its complement is visibly independent in H. That is, from these collection of columns, we can find a substencil as visibly full rank. So from DGGW20, it follows that QLCC stencils also satisfy the same lower bound by their dimension up by their rank upper bound and this rank nullity theorem that we show. And so therefore, the visible rank of LCC stencils also also recovers known bounds on LCCs. Moreover, by our LCC stencil construction, we can also find not just only LCC spanoids, but LCC symmetric spanoids that match known bounds. Okay. So in summary, we've introduced a combinatorial framework that we call stencils to study the redundancy of DRGP codes in LCCs. And we show that there's a natural combinatorial parameter that we call visible rank, cannot improve on known bounds or DRGP codes in LCCs. And we introduced a tensor product that recovers the known bounds for the DRGP codes, but does not improve on LCC bounds unless you take a polynomial tensor power. And then finally, we show that the visible rank also recovers known bounds for LCCs by some rank nullity theorem between stencils and symmetric spanoids, and then we just realize the result by DGGW20. So all these combinatorial parameters also recover all the known bounds for DRGP codes in LCCs, but they do not easily improve them unless you take a very high tensor power. So these are all the references that we use in the talk, and so thanks for watching.